at position 2 or 3 or 4. So you get a lot more configurations. So the moment you have defects, or for example, you have a repetition of AB, AB, AB kind of structure. But why do these AB have to arrange like AB, 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 AB? One of them could be BA. If that's also a possibility, then I could again have lots of these different configurations or microstates. And if I have that, then W comes out to be more than 1, and my entropy is not 0. Now going back to yesterday's example, what we calculated was the change in entropy. Right? The change in entropy was R log 2. And what happened was, you had a volume V. Now you have a volume 2V. So if earlier you had n number of microstates available, you have 2n number, and the change would be just log 2. Right? Okay, so that essentially brings to the discussion that we had a moment ago. What it says is the third law, that the entropy of perfectly crystalline solids at 0 Kelvin is 0. Yeah, in a sense it says, okay, forget about 0 Kelvin. No way you're going to reach that. Yes, please.
Randomness is defined only on the basis of configuration, or it is defined if configuration remains same but added up?
So that's why you go down to 0 Kelvin so that there is no motion. There is no temperature. There is no thermal motion.
So if we consider that example that we just now, that will add now, right?
So the gas, what you're doing is you're just calculating the total number of microstates and see what is the change. Now your microstates are doubled, and that is the log of 2n by n. Or log of 2n minus log n. Okay, so that is fine. Then we move on to describe the system, and this entropy, although it becomes clearer and clearer as you go on with it, but then there are much easier ways to see if the system is spontaneous or not, if the change is spontaneous or not. Okay, and for that we'll again start with the Clausius inequality. Now what does it say? So going back to Clausius, yes? So what it said was ds is greater than or equal to dq by t. So ds minus dq by t is greater than or equal to 0. Okay, and I also know that dq, or I could write like du is equal to dq plus dw, and if I say my volume is constant, then it just gives me dqv. So at constant volume I could write ds minus dqv by t, or I could write minus du by t is greater than or equal to 0, or in other words t ds is greater than or equal to du. Yes? What it gives me? Always at the back of my mind I always know that it's constant volume. Now this gives me two conditions. So the Clausius inequality is another statement of the second law, and it's telling me work spontaneity. So we are trying to evaluate some more conditions of spontaneity which are easier to measure, understand, whatever. So there are two conditions which I get over here. One is ds at constant volume and constant internal energy is greater than or equal to 0. So if I put du equals 0, or the other way around, du at constant volume, constant entropy is less than or equal to 0. So look at the two things. The first one you have seen a number of times. The first one says that, okay, when I'm talking of ds, one should remember that this is entropy change of the system only, right? Not of the surroundings. So the first one, what you see, says that, well, you keep the volume constant, you keep the internal energy constant, which means the heat is not supplied across. So it's an isolated system kind of thing. The change in entropy is greater, but that's the statement of the second law. The change in entropy for an isolated system always increases, does not decrease, whatever. The second one, it says that for a spontaneous process, the change in internal energy at those conditions, constant volume and entropy, should be less than 0. That's a very misleading way to think of it. If I do that, although you should remember that S is only the entropy of the system. It's not it does not include the entropy of the surroundings. But what I want you all is to think of any spontaneous process as an increase in the total entropy, right? So if you think of this, that the internal energy goes down, and that's why a process is spontaneous, that would be wrong. Okay, but if you know that your volume is constant, the entropy of the system is constant, and then the internal energy goes down, then everything is fine. Why? Why? Because if the internal energy goes down at a constant volume, heat is released out of the system, which means heat goes out to the surroundings, which means that the entropy of the surroundings increases. And that increase in the entropy of the surrounding, when your entropy of the system is 0, change in entropy of the system is 0, means that your delta S total is going to be positive, right? So, although if you rigorously remember du at constant volume, constant entropy of the system is less than 0, it's fine, but the understanding is still the basic thing, the second one. So the entropy of the system is constant, but the entropy of the surrounding increases, because if du goes down, it means heat is given out of the system. Volume is constant, so no work is being done, only heat is being exchanged. One thing what I should have mentioned earlier is that there is no additional work involved. Okay. So let me just write over here as well. No